350,000 tons of ultra-pure water, 6,000 scientists and engineers, $3 billion, 50 years of relentless searching. So, what's the result? Hi, I am Firuza, and this is Bold Science with Firuza. Today, you'll hear one of the strangest, most expensive, and most quietly downplayed stories in physics. A story about how scientists spent decades hunting for a phenomenon that no one has ever actually seen. This is an investigation into the hunt for the decay of the proton. Yes, that very proton that makes up almost all the matter around us. You, me, and the screen you are looking at right now. And here's the key question. Why would anyone even want the proton to decay? The answer lies not in the properties of the proton itself, but in the structure of fundamental theories. Within grand, unified theories, the proton is no longer an absolutely stable object. The quarks inside it can transform into one another via superheavy force carriers. Such a process inevitably violates baryon number and, as a result, leads to proton decay into lighter particles. That's why proton decay was considered not an exotic possibility, but a direct and testable consequence of these theories. All grand unified theories predicted proton decay into a positron, the electron's antiparticle, and a neutral pion, which almost instantly decays into two gamma rays. In other words, bangs, the particle flies apart. If this were happening, we would see a flash of Cherenkov radiation, a blue glow in enormous water detectors. The problem is no one has ever seen it. The first searches, zero results. The first attempts to find proton decay began back in the 1960s and 1970s. These were laboratory experiments at universities in the United States, Europe, and the USSR. Researchers studied nuclear emulsions, mica plates, and ionization chambers, trying to spot the positrons and gamma rays predicted by grand unified theories. The total global cost of this work over a decade is estimated at about $520 million in the money of that time, roughly $50 to $100 million today, or even more. Years of work, thousands of analyzed events, and complete silence. Not a single hint of decay. After a decade of such fruitless efforts, physicists decided to go big. In the United States, a giant detector called IMB was built. It operated for 9 years, from 1982 to 1991. About 2,000 tons of water were lowered deep into a mine. Inside were 2,048 photomultiplier tubes. Why water? Because it's an almost ideal detector. Water contains a huge number of protons. It has a high refractive index. It is transparent to photons. Light travels more slowly in water, only about 225,000 kilometers per second. So if a charged particle moves just a bit faster, it starts to glow. This is Cherenkov radiation, which the photomultipliers can see. It seems obvious. If even a single proton decayed, we would notice it. But we didn't. Japan, another Titan-scale experiment. At the same time in Japan, the Kamiokande detector was built. It ran even longer, 13 years, from 1983 to 1996. 3,000 tons of water, thousands of sensors, all for a single event, proton decay. The result? Zero again. A new scale, Super Kamiokande. Scientists decide, maybe we just need more water, and they built a new facility, Super Kamiokande, which has been operating from 1996 to the present day. Now it's 50,000 tons of water. To grab the scale, that's like 20,000 fire trucks completely filled with water. All of this enormous mass sits in a single underground tank. And there is more. The water has to be perfectly pure. So in Super Kamiokande, it undergoes continuous multi-stage purification, including ultraviolet irradiation, so that even bacteria don't glow and interfere with the measurements. The water used in Super Kamiokande is 1,000,000 times purer than drinking water. It's far purer than the water used in microelectronics and pharmaceuticals. Now pay attention. Even if the proton lived 1 billion times longer than the age of the universe, even in that case, Super Kamiokande should have caught a decay. But as you've probably guessed, it didn't. This race has cost humanity staggering amounts of money. How much the United States spent on the IBM experiment is still unknown. Those figures were never published. Japan, however, did disclose the numbers. The construction of Super Kamiokande cost about $100 million in early to mid-1990s dollars. Adjusted for inflation, that's roughly $240 to $150 million today. And the next project, Hyper Kamiokande, is officially estimated at 64.9 billion Japanese yen, which is about $600 million in today's dollars. Enormous sums, decades of work, tens of thousands of tons of water, and not a single confirmed proton decay. That really makes you think about which theories we continue to support and at what cost. Nearly 50 years of searching, billions of dollars, zero decays. From the 1960s to today, not a single confirmed event. Physicists keep observing, keep expanding the detectors, keep increasing sensitivity, but facts remain facts. Proton decay has not been detected. And this raises a very simple, very sharp, and very honest question. If a theory predicts an effect, but the effect doesn't exist, is it a theory or a fantasy? How much more money, how many more decades, and how much more water are needed to admit the obvious? If nature doesn't confirm your hypothesis, then the problem is not with nature, the problem is with the hypothesis. And a final question for you. What do you think? Does a grand unified theory, with its prediction of proton decay, remain scientific or no longer? This was Bold Science with Firuza. Thank you for your attention, your support, and your interest in real physics. Physics grounded in reality, not in invented mathematical constructions.